Everybody, today I'm going to publish on the folio the pre-lab for next week, so you can start working from now. I'm not going to give any more extension for any more pre-lab. I have been the last 3 pre-lab making extension on day. So if you want to do it on time, start on time. You don't wait to the last minute. The pre-lab is going to be in lab class. So you got to your class. 2 problems on the pre-lab and the lab itself. They are a small problem. 1 problem, solving differential equation using Laplace. So you do by your hand, that's easy. So you got to practice partial fraction. Second part will be like to find Laplace transform for a signal that's defined over a specific period. Not from minus infinity to infinity or from 0 to infinity. So I will give you a hint. It's a property of delayed signal. So if you have unit step u of t, we know that the Laplace will be equal to 1 over s using integral method, or using the table, it's 1 over s. What about if we want to have unit step but delayed by 3 units, start from 3, not from 0? So how you define this function? You define it as that if you go to the x of t, that will be equal u t minus 3. Laplace of this one will be the same one as before, x of s multiplied by e to the power of the minus the delay, e minus 3s. What about if you have different function, not unit step, and you're going to have one like that? Let's say, what's the Laplace for the function e to the power minus t ut? That would be equal to, from the table, 1 over s plus 1. Let's make this one 2 plus 2. That's the function, and start from 0 because you have multiplied by u of t. Now I'm going to ask, let me just make this clear, that's equal to e to the power of minus 2t. So you got 1 over s plus 2. Remember, all the function we are dealing with unilateral, it means it's starting from 0. It is Laplace from minus infinity to infinity. We are focusing in this course on this simple one, from 0 to infinity. What about if we want to find Laplace for e to the power of minus 2, and the t is shifted by 3 units? When you have something like that, the shift in the step and in the function itself, like e to the power of negative 2t, every t shifted by 3, and the step, the t is shifted by 3. You cannot have like, what about that? Can you do that? No. The rule said that everything is shifted. So how you will do the Laplace for this one? You get the same one you got before, which is x of s, that's our x of s, 1 over s plus 2, and then you multiply by e to the power of the minus shift, which is equal 3s. That would be the answer. You can write like that, e to the power of minus 3s divided by s plus 2. You will have one problem in the pre-lab on something like that. So I explained for you, you have idea about it, it's not strange. Differential equation, we solve one good example. So that would be your pre-lab. You can start from tomorrow, be tonight. I mean, publish, you don't have time, but that's the two things on the mask. And when you go to the lab after that, you are going to solve both of the question, differential equation and Laplace transform, using function in MATLAB that help, like how to find the inverse using MATLAB, just one command, like the last lab. Okay. Any more question on that? All right. So now let's start the the topic today. We did finish analyzing signal continuous time signals. We did Fourier series. We did Fourier transform. We did Laplace. We are not ignoring discrete type signals. We are going to start now dealing with it. So we did continuous time Fourier series for the signals continuous time. And let me refresh your memory. So if you have x of t and you want to find the spectrum or in the frequency domain using continuous time Fourier transform, we'll call it x capital of omega will be equal to the integration from negative infinity to infinity x of t e to the power of minus j omega t dt. That was the continuous time Fourier transform. And we could also find the Fourier transform for these signals using we call it, Fourier transform pairs. You look for the table, that's the function of time, that's the corresponding one in frequency domain. For example, I go and I look for the table. I don't have the table. See, I'm looking just for the table for the continuous time Fourier series. So I'll give you just a couple of examples before I start the discrete. Yeah. You have the continuous time? No, that's Laplace. Yeah, that's Laplace. We have those pretty much everything. That's okay. Short one. Yeah, that's right. There's a long one. Yeah. That's for something specific. Need the more exponential measure. Yeah, that's good. Thank you. Well, so in the table here, I'll pick some example. Like when you have if x of t equal 1 in the table, x of omega will be equal to 2 pi delta omega. And let me pick another one. Yes, here. If the function equal e to the power of j omega naught t, then the corresponding frequency equal to 2 pi delta omega minus omega naught. I will take one more. If you have cosine x of t equal cosine omega naught t, so the corresponding Fourier transform equal 2 pi delta omega minus omega naught plus delta omega plus omega naught. So I picked just 3 examples. Different. There's one constant value, one has a exponential function, has imaginary, and then cosine. So that's 3 different. So that's, you can look at it and then you adapt your problem and you solve. Okay. We did that for continuous time. And we did Laplace, which is more general than continuous time Fourier transform. We are going to do the same thing with discrete time signal. We're going to do discrete time Fourier transform. Discrete And that's our topic today, discrete time Fourier transform, and write like discrete time Fourier transform. Okay. And we are going to have something similar to Laplace transform called Z transform. Then we will have application. So we're done with that. Okay, how we'll do discrete time Fourier transform? You have to look at the one that we did. If you are dealing with a continuous time signal, usually we use integration. When we are dealing with discrete time, we use summation. So I'm going to convert this to summation. Let me write it here also for them. X of t, just to compare, is equal to the integration negative infinity to infinity, x of t, e to the power of negative j omega t dt. Now, I have x of n. That's our discrete time, the sequence. We don't have x of t. We have only this. So what we'll do? Well, we have x capital. And we still can write omega as we did here, but we are going to use the uppercase omega just to differentiate between the continuous time signal and discrete time signal. Some textbook use e to the power of j omega t, but no single textbook use the same thing. They have to differentiate by something. So I will say I'm going to use the same. By the way, this is not x of t, that's x of omega. That's x capital for me. So I'm using the same omega, but just one capital. So that'd be equal to, and instead of integration, I'm going to have summation. All right. And I have x of n multiplied by e to the power of minus j, and instead of omega, I'll make just omega. It's the same thing. Instead of t, I'm using n. And of course, I'm not integrating, so I'm not writing dt, but the variable is n. It will be from negative infinity to infinity. So it's so simple. Very similar to the one, except only integration turned to summation. I don't have t, I have n instead. That's all. So let's look what we'll get. There are some kind of characteristic of this transform, but first, not every signal you can find Fourier transform, even continuous signal. It has to be limited. So what is the condition for this one? The condition is this summation of the absolute value of this sequence from n equal negative infinity to infinity, before you multiply by e power minus j, this function of this signal itself should be limited, should be less than infinity. If you add all of them and you're getting infinity, so you cannot find this firm. So that's a condition. It's the same condition like for the continuous, but we were using integration, and the integration limited to certain value less than infinity that you can perform the transformation. Okay, what are the characteristics of this transformation, x of omega? Now I'm talking about that, the characteristic of this one. Well, is it the result, is it real or complex? Complex. So x of omega in general is complex valued function. It's a function. In general, it's complex. Even x of n is real. Why we expect that? We expect that because you multiply by e to the power minus j, which is complex. All right. The second thing, it's periodic. The result is periodic. So x of omega, periodic function. Function of what? Omega. And what's the period? 2 pi. That's why when they define the spectrum, it's enough to define the spectrum over 2 pi period. You can define it from 0 to 2 pi, or you can define it from omega negative pi to pi. It's enough. Why? Because it's going to be repeated every 2 pi. And that's very important characteristic. So you can write, since it's periodic, you can write x capital omega plus 2 pi is equal to x omega, because period. All right. So actually, if you know the corresponding continuous time signal for the sequence that you under investigation, you can easily transform it to Fourier transform. What does it mean? Means, let's say, for example, you have this function continuous equal 1. Let me take this and be a good revision for it. I will take this function signal. So how you sketch x of t equal 1 continuous? You will say that's the time axis, and that's x of t. It will be just a line, straight line, horizontal line at 1. That's how you sketch the signal. Well, how you sketch x of omega? Okay. It would be like that. This axis will be omega. And how we sketch delta, the impulse response, to be like a straight line, short line, and has arrow. It means the amplitude is infinity and is located at 0, because delta omega only. So you come at omega equals 0, and then you make like short straight line like that, and just make an arrow like that. That's mean the amplitude is infinity, but you write it is equal delta multiplied by 2 pi. That's the spectrum. So when you have a fixed value equal 1, the spectrum is equal 2 pi. Delta is like you have a line, or you have an impulse at omega equals 0. Yes.
So is the value 2 pi or infinity?
2 pi.
Okay,
so it means if you have a short period, like epsilon 0.1, like if you have something like that, how we make the practical impulse. Let's say you have, if you have 0.1, the width 0.1, very short, 0.1. So what is the height?
Because you multiplied it by 2 pi, it's 2 pi, right?
Yeah, but what's the height here first? That's unit impulse.
Oh, just the impulse that should go up to infinity, right?
Infinity if the width is 0. If the width has like 0.1, what would be the height? 10. Why? Who's it 10? Good.
The area is 1.
Exactly. Because the area is equal 1. That's the definition of a pulse. So every time, if you have 0.01, so you have 100. If you have 0, it will be infinity. But practically, you cannot find something has 0. This is the ideal, but practically it has width. So if you want to have 2 pi, you multiply 10 by 2 pi, if the width is 0.1. Okay, so then after that, if you multiply 2 pi here, you multiply 2 pi here. Right? So that's the meaning of the spectrum. So when you have constant value equal 1, the spectrum, the frequency 0. What does it mean the frequency 0? Omega equals 0. What does it mean? What does it mean at the frequency omega equals 0? What does it mean omega equals 0? No, omega equals 0. What does it mean? What does it mean omega equals 0? Just the mean. I don't want any value, just the means. I say omega equals 0. So what does it mean? What does it mean? What does it mean? Why?
Like it's zero.
Huh? No. What's omega? Frequency, right? What does it mean the frequency equals 0? What does it mean frequency equals 0? What is DC? DC. DC battery. You are electric engineer, right? Not mechanic. Okay. So when you have a battery, the battery DC, it means that no frequency, 0. All right. If you have frequency equal 50 hertz, omega will be equal to pi f, 2 pi times 60, be 314 radian per second. So that's the frequency. So when you say at omega equals 0, it's equal to 2 pi delta omega, it means that the spectrum of this signal and time, it will have only one component, DC, which makes sense. Because when you have one like that, what does it mean? It's DC. So it makes sense. Yeah. So it has pulse at DC and the height of it at this one, 2 pi. All right. So, and we say only why, and we use delta omega. It's very important. It means just add only omega equals 0. You will have the spectrum equal to pi. Only add the DC component. All right. So, I mean, you have to understand the meaning of what's happening, not just, I mean, put numbers and that's it. No. Well, let's now do that. What about if you make this function discrete? Can you make this function discrete? This one? Yes. How will you do it? Huh? Yeah, bunch of vertical lines separated by the sampling. If you have sampling, okay. So let's sketch the so we'll do the discrete. So this axis is not going to be time anymore. It's going to be n, and I will have uniform. Let's say there's 0, 1, 2, 3, and so on, -1, -2, -3. So it would be like the height is 1. And you just continue like that. And the height of each one, you make a circle like that. It's each one. I have questions to make sure you understand. What is the difference between these two signals that I just sketched? Let me write down the. Yeah, let's say that that's I write here 1.
Oh, that one has at the end location, that value is 1, but the other one, the right one is infinity.
So how you write to express this one? Let's call this is 0 and call this 3. How you express the signal? At 0.
Just 3 delta. That's just 3 delta.
3 delta?
No, that's the
This is when you have a vertical line with arrow, it means it's impulse.
Yeah. So delta,
it's impulse, yeah. So that's impulse, and this impulse you write it like delta omega. If this is omega, will be shifted by 3. Shifted by 3 to the right. But this one has a magnitude equal 1. This one has a magnitude equal 1. All right. The magnitude is equal 1. Like what I'm doing here, all are ones. The height is equal 1.
Oh,
The height is equal 1. Yes. Okay. Now I did sketch the equivalent discrete signal ones for this continuous. We can do, if you can do the integration, it will take a long time. But if you know the Fourier transform for the equivalent continuous signal, you can do it very easily. Why? Because we said that the Fourier transform of a discrete time signal will be a periodic signal function of omega and repeat it every 2 pi. So all what you're supposed to do, you take this function that you got, x of omega, and repeat it every 2 pi. And you got it without doing the integration. Well, can you sketch it to understand it? Yes, well, let's sketch it. We'll have, let's call this again the same omega. I'm using like that. And then I have one, I sketched the one I have at 0. That's the first thing. And that's, 2 pi delta omega. Then I repeat every 2 pi to the right, to the left. So I have one at 2 pi. I make the same thing. 4 pi, the same thing. Don't sketch too much, just a couple of them. Minus 2 pi, minus 4 pi, and continue. And then try to express. But let's just before, since we agreed that the discrete time Fourier transform will use capital omega or uppercase, so we'll just replace this small omega by the big one. So I have omega. All right. So how do you write this sequence? Do you know how to write this sequence? Train of pulses? Well, I will write x of omega equal. There are many. Just I will start from this one. How you write this one? Let me write the one in the middle. You know the one in the middle. It's 2 pi delta omega. What about the one just here? That's shifted to the left. How you write? Anybody know? 2 pi delta omega. What the? No, plus. Minus or plus? One to the left. Plus, okay. Plus 2 pi. And then every time you are minus 2 pi, then you comes here, you have 2 pi, the one to the right, 2 pi delta omega minus 2 pi, and you continue, right? Now, if you want to write this as a summation, you will have, in general, say 2 pi delta omega, and this, look at this 2 pi. It's, you can say minus 2 n pi, where n from negative infinity to positive infinity, right? And you check what is n here, negative 1. N is equal 0, n is equal 1. Check the formula that you have. If you put here n equal negative 1, what you get plus 2 pi. Because you're starting from n equal negative. And I know when I have the negative, I have positive. Yeah. And then when you put the n equal positive, like n equal 1, you get minus 2 pi, which is right. You just can put in the top, as I did here, I remind myself, n equal negative 1, n equal 0, n equal 1, and then try to figure out how we put the sign. When you look at the table for discrete time Fourier transform, you will find this is the result. I didn't do integration, just I used the result. It's a periodic signal of 2 pi, yes.
So is it a coincidence that in this example that our period is like it goes the increments are 2 pi, but
not by accident. It's all discrete time Fourier transform periodic signal of 2 pi.
But the delta, the part in front of the delta is also 2 pi.
No, this is by accident.
That's by
you don't, yes.
Okay,
we'll have examples in 2 pi. The important part, it's repeated every 2 pi.
It is
the height, it does not affect.
Okay.
Yeah.
That's what I want to double check.
Yeah, that's good. Yeah, because yeah, we'll have some function doesn't have 2 pi. Sometimes we have pi and things like that. Not necessary. Because if I ask, for example, like if the height is not 1, if the height is equal 10, for example, so we'll find this one become 20 pi. Let's take one more example. We did that. We'll have the exponential one. Example 2. Example 2, where we need to find what's the continuous time for e to the power of j, and let's say alpha t. If I look at the table for the continuous, I found out that x of omega is equal to 2 pi. You see, we have 2 pi from the beginning. 2 pi delta omega minus alpha. Let's take numerical value as better. Let's take numerical value. Let's take this example. Let's say alpha is equal to 3. So you got omega minus 3. So now I want to do the discrete form will be equal x of n is equal e to the power of j 3n. And the question now, I want to find x omega. I'm going to use the same technique. Very similar to the other one. All right? Very similar. Go ahead and do it as a quiz. Show me what you do.
So you want for us to solve the case of x over x omega?
Mhm.
Did you want like the picture of the graph too?
No, you don't need to. It will help you to find it, but I just need the expression. Two minutes. Well, it's the same way. I'm going to add 2 pi, subtract 2 pi. You can sketch if you like. I prefer to sketch it just to understand it more, because I like, visualize what's happening. So I have a pulse here, delta omega minus 3, it means at 3. That would be 2 pi delta omega minus 3. So if I do the discrete one, will be the same one, right? I'll put the original one. First, I'm going to change from lowercase to uppercase. And then I put a 3, the first one. And then I'll write just 1 enough, even, just to remind myself. Then I have 1 at 3 plus 2 pi. I have another one at 3 minus 2 pi. You don't have to sketch all of them. Or usually I do that. And I remind myself, this is at n equal 0. That's an n equal 1. That's an n equal -1. Right? This is my first one. So I will say, if you write it, you will say that x of omega equal to this one in the middle, even right in the middle one, in the first, if it's easier for you, the middle one is equal to 2 pi delta omega minus 3. So the one before that, I will subtract 2 pi. So I have 2 pi delta omega minus 3 minus 2 pi. And then the one to the right, when n equal 1, will have 2 pi. I'm looking for the original one. Delta omega minus 3 plus 2 pi. Of course, I got to change the all omega small to omega capital uppercase. So I have omega, omega, omega. Now, obviously, omega minus 3 is everywhere. It has to be written. The whole issue, it's minus 2 pi k or plus 2 pi k. Usually it's minus, by the way, because I start from n in negative, usually. So I don't have anything think about. So I say the summation n equal negative infinity to infinity, 2 pi delta omega. I just write the original one here. I can do it in 1 second. The original one, and I say minus 2 pi k. 2n pi. I'm using n, so 2n. Of course, you can write, instead of n, you write k, it's okay. L, m, whatever, you put it there. So it's very easy. If I look at this problem, I'll just, since it's one signal, one pulse, I'll take the same thing, I'll say minus 2 pi k. Capital, they are right, yeah, with keeping this capital omega. So what's the difference between this one and this one? Adding the term minus 2n pi. That's it. Every pulse you have, you just do that. Yes?
Why is it minus 2n pi instead of plus 2n pi?
Because when you start, when you have n negative 1, if you put n negative 1 here, what you'll get? You get plus 2 pi, right? Which is the, which this one should be like, actually, a second. That's expressed like that, right? The one to the left, when shift, b plus. So when you put here n equal -1, you will get omega minus 3 plus 2n pi. When you go for n positive, like n plus 1, you'll have omega minus 3 minus 2 pi. Like the last example, when we did here, we say minus 2n pi. Why? Because when you put n equal -1, what you'll get? We get omega plus 2 pi, which is the signal. The signal here. How we write the signal? Plus 2 pi. Because any shift to the left, you make it plus, right? So you flip the sign. Start from the left to the right. That's always like that. Always like that. So actually, it doesn't take more than 5 seconds. You just add the term minus 2. If we take the last example, and then we'll find how we'll do the integration. I'll take cosine. So x of t equal cosine, let's call it omega naught t. So the Fourier transform of this one, according to the table, is equal to pi delta omega minus omega naught plus delta omega plus omega naught. That's the cosine. Look at the cosine. So what you'll do if you have x of n equal to cosine omega naught n, without sketching, I can do it. Because if you look at one signal only, just cover this one right now. If you cover this a little bit, just, I mean, temporarily here, where you say I am having only one signal, I know that x of omega will be equal, I have pi, I don't have now I should have summation. So I have the summation, and I have n minus infinity to infinity. Then I don't put 2 pi. I just look at this constant. I found this time is pi, I write pi. Then I have delta, I write the same thing, delta omega minus omega naught. Then I will say minus 2n pi. Now let's take pi as a common factor. I think the second one will be delta omega minus, that plus omega minus 2n pi. Yes. Yeah, capital. Yes. You're right. I don't know why I'm just, yeah, has to be capital. You're right. I replace this omega and this omega by capital omega. And this is, let me make it clear, that's plus. So there is 1 minus 1 plus. So just I take the expression, especially this is in delta, just in pulse. It's easy to do that. Once you have delta, just do it. So it's easy. I don't have to sketch it. But when you sketch it, just you have understanding. Let me sketch the continuous. Because look to me, you guys didn't look at the physical meaning of the spectrum itself. When you look for this, if you have a cosine omega naught t. Let's say omega naught is like equal 314 radian per second. I think, or 344. That's the corresponding 60 hertz. I think 344. You have 60 hertz. You have 60 hertz, and you want to find the corresponding omega naught, or say 2 pi f, 120 pi. So 120 times pi, it will give you 376. Okay. So that's 376. So if you have this one, x of t equal to 377 t, that's mean you have a cosine wave or sine wave, and this cosine has frequency 60 hertz, which is corresponding to 377. What is the spectrum? And by the way, I'm taking the amplitude 1 and negative 1. The spectrum, according to Fourier transform, is equal to 2 pi delta omega minus what? In this case, x omega equal 2 pi delta omega minus 377, right? So when you sketch this, I have only 1 or 2? 1 only. So when you sketch it, it will be like at 377 positive omega, I have pulse height 2 pi. It means that this sinusoidal wave that has frequency 377 will have in the spectrum only one signal at this frequency, because we're taking pure sine. The Fourier transform is very nice if you have some kind of weird waveform. It's not sine, it's not constant, something like square, triangular. Then you want to know what the component inside. So if you make triangular, for example, if you make square, so what embedded inside that does have what, at what frequency do you have? But I'm giving you a simple example so you understand it makes sense. If you have cosine 377t means it's only periodic of one frequency, the spectrum will be only this frequency. When you have a DC, you have only at omega equals 0. What do you have? Square wave. Try to do it. You will see you have variety. When you did the rectangle, what you get? We get sinc function, which is like continuous. Like I mean, you have at every single frequency, you have some component, but it's big in the middle and then decreasing every time when you go to high frequency. That's the value for it. So that's, I mean, how you do the discrete Fourier transform using the continuous time form. Now I'm going to use the integration. Use the integration. I'm going to give you a list of formula how to get closed form for common series, especially geometric series. There is one I want to give it to you before I start this example. If you have the sum of r power n, and n start from any number n1 up to n2, so it's given like r power n1 minus r n2 plus 1 over 1 minus r. They have ugly expressions, but I mean, you don't have to prove it anything. Just use it to simplify any expression here. Example, if you want to find the sum, they are very helpful actually. To n and n from 0 to 3. You want to get the sum of something like that. If you don't want to use the formula, intentionally I got like from n equals 0 to 3 something simple, so you will get it. I will say n equals 0, 2 power 0 plus 2 power 1, 2 power 2, 2 power 3. So what you get? You got 1 plus 2 plus 4 plus 8. 2 and 8 is 10 and 5, 15. So the answer is 15. It's easy because you do it from 0 to 3, you substitute. But when you have from n equal minus 100 to 100, you will not do that, right? So you'll use the expression. Let's check if the expression is right. So in this expression, I'll say the sum from n equals 0 to 3 to n. My r is equal to, so I'll say r is equal to n1 is equal 0 minus r is equal to n2 plus 1, 3 plus 1 will be equal 4, divided by 1 minus r, 1 minus 2. 2 power 0 is equal 1, 2 to the power of 4 will be equal 16. 1 minus 2 is equal negative 1, so it'll be negative 15, divided by negative 1 is equal 15. Yes, same result. So that's the right expression. So this is one important expression to simplify series. Okay. Now, why I did that, we don't have integration, but because we have summation, so you will be exposed a lot. You need to do that. Let's take one example that it will not help you to do what the nice technique with that. What about if you have a function not in the table? So what you'll do, you'll go to the integration. I'm sorry, to the summation. So this example, how to use summation. But somebody might ask, can I change if the discrete signal, if the given discrete signal, it's nice that I can convert to continuous, and then yes, you can, of course. If you can convert to continuous, and it's handy with you that you have the continuous time Fourier transformation, yes, use it and then do what we did. But in any way, this signal that's given x of n, that's example 4. Equal to 2 to the power of n, when n from 0 to 4, and 0 otherwise. I just like always, I mean, to sketch the signal to see what look like. That's like if you have, that's n. And at 0, 2 power n is equal 1, right? So you have something like that, 1. And at 1 will be equal to, will be the double.
and at 2 will be 4. Oh, I don't have enough space. All right. 2 at 3 will be equal 8. And at 4 will be equal 16. Can go up 16, right? And before that, 0, 0, 0, 0, and 0, 0. Okay, so that's the signal, discrete. Of course, you can convert this to continuous if you replace n by t, but let's just do it using the summation. So according to the rule, we'll say that x of omega equal to summation should be n from minus infinity to infinity, but here from minus infinity up to 0 is equal 0. So I will say from n equals 0 up to what? N equal 4. That's what I have. Before or after that is equal 0. And the function 2n. If you don't have the function given like that, you can just write it down as a series. 2n to the power of what? E minus j omega n. Now that's what I'm talking about. Once you do that, if you don't have useful formula or expression that can get the summation, you'll be stuck. So I give you one summation, the summation of r power n. So I want to express this r power n. Always think about that. So how you do that? How you express this expression like r power n? Any idea? Okay, I will say 2, that's the power n. I have e minus j omega times n. I can make it power n like that, right? And then this power n, I put them together and in one package, and they'll make it power n. 0 to 4, 2 times e minus j omega, the whole power, oh, sorry, the whole power n, right? 2 power n. Let me, if you have something like that, how we write it? Can you do it like that? Yes, you multiply the number because you have common power. All right. Why what? N plus n, why? No, n plus n if I have the same number. Look at that. If you have 2 power 3 and 5 power 3, both they have the same power, so we'll say 2 times 5, the whole power 3. But if you have 2 power 3 times 2 power 5, that's different. If you have the same base, you'll say 2 to the power 3 plus 5. All right, thank you. Well, so now this is your R. Once you do that, now you know that this is your R inside the bracket. So you will say that's equal to the summation R to the power of n, where R is equal to 2e minus j omega. Now, the formula that I gave you before would be very useful. That will be your N1, that will be your N2. So you will have R, let me write the formula, R N1 minus R N2 plus 1 over 1 minus R. Now just I substitute. So you have R power 0 minus R power 5 over 1 minus R. That's 1 minus R power 5 over 1 minus R. Now you're ready to put this ugly formula of R, 2e minus j omega power 5. That's power 5 over 1 minus 2e power minus j omega. You can write the top 1, you get it back. If you have, you will have 2 power 5 times e minus j 5 omega. It's better do it in this way. 1 minus 2 E minus J only omega, and 1 minus what's 2 power 5? 32 E minus J 5 omega divided by 1 minus 2 E to the power of minus J omega. That will be the expression for the Fourier transform of the signal that I give it to you. It's a complex, as you see. We said from the beginning that the result in general complex. Sometimes you can get real and the measure equals 0, but this is in general. All right. How to sketch this one? You split it into two parts, real and imaginary. Split into real and imaginary. Computer is very helpful in MATLAB that you can put this formula and then find the real and imaginary, but we got to learn how to do it by your hand too. So how can you find the real and imaginary? Well, you change it to use Euler form, which is say that E to the power of J theta equal to cosine theta plus J sine theta. So what you will do in this formula, you are going to say that the top part, we'll call this N and D. Joseph, the top is called N, the bottom called D. Numerator or denominator? I remember from Laplace, you know. So you have N will equal to 1 minus 32, and this E will be cosine 5 omega minus J sine 5 omega divided by 1 minus 2 cosine omega minus J sine omega. Now, oh, that's the D. So now you will say that collect the real parts together. So you have 1 minus 32 cosine 5 omega minus J 32, because 32 is common, sine 5 omega divided by 1 minus 2 cosine omega real part, and the imaginary minus, oh, that's positive. Negative times negative is positive. The same thing, negative times negative is positive. J2 sine omega. So that will be your x of omega in general, but it's getting better now. You have real and imaginary, and you can get number. Let's say now we want to find the spectrum of omega equals 0. By the way, this function that you have it, or this sequence, it's not constant, it's not sine wave pure. It's so I expect it's going to have mix of frequencies. So just I'm interested, what's the DC component in this spectrum? If you want to find the DC component, so what is the value of omega? I just want to check if you guys still remember. So, but now omega equals 0. That will be the DC component. X of 0 equal 1 minus, what's cosine 0? 1. So you have 1 minus 32 plus J. What's sine 0? 0. All right. Let's talk in the one at the bottom, 1 minus 2, and again you have 0. So it's equal minus 31 divided by minus 1, 31. Okay. So the DC component, its spectrum will be equal to 31. Or doesn't have imaginary part. So there's no angle for DC, right? It's a constant. So I'm saying the component in this discrete signal has component, DC component, and its amplitude is equal to 31. Well, maybe you are interested in some other frequencies. Let me check for pi over 2. What about x pi over 2? I'm picking omega equal pi over 2. So I will have 1 minus 32 cosine 5. Let me take something nicer. Pi over 2. Pi over 2 equal 5 omega. So no, I will say pi over 10. All right, let me pick pi over 10. So x of omega equal pi over 10 equal the top part 1 minus 32 cosine 5 omega. What's 5 omega in this case? 5 omega. 5, yes, 5 will be 5 times pi over 10 equal pi over 2. Good. So what's cosine pi over 2? 0. All right. So you have 1 in the top part, 1 minus 0, 1. So that will be 1. And what about the other side? J32 sine pi over 2. Sine pi over 2 is equal 1. So you have plus J32. All right. Let's get in the bottom part. 1 minus 0 be 1 plus J sine oh no, that's not that's cosine omega only, right? What's cosine pi over 10? No, it's not. It has a value. We need to find cosine. That's 1 minus 2 cosine omega, and omega is equal to pi over 10. Pi over 10 in degrees, what does it mean? 18 degrees. Okay, so it means like 18 degrees. I'm going to substitute now. I have 1 minus 2 times cosine 18. Cosine 18 times 2. That will be equal to 1.9 plus J 2 sine 18. Sine 18 times 2. That's equal 0.618. So the result will be 1 plus J32 divided by minus 0.9 plus J.618. You get complex number and you can get its real and imaginary one. I can do it even in the calculator. I don't need the MATLAB. I'll just use the complex and I will give you the result. I will have 1 plus 32i plus 32i divided by minus 0.9 plus 0.618 I. Okay, that's the result. I got real and imaginary. I got 15.8 minus J 24.7, and I can convert it to polar form. Shift complex 3. I got 29.3 and the angle negative 57.3. So at this frequency, 18 radian per second, you will have amplitude 29.3. You have a sine wave in this sequence, in this signal. It has DC equal 31. It has sine. It has like a sinusoidal wave because give me magnitude and angle. Sinusoidal wave. Its amplitude equal 29.3, shifted by negative 57.3, and you can go ahead and get. It will give you at any frequency the component that you are interested in. Okay, so that's the benefit of making Fourier series in general, continuous or discrete, but to have the chance today to explore it with both. Of course, in this signal, obviously it's continuous. If you look at the signal we got x of omega, it's continuous. What does it mean continuous? It's continuous function of omega in this case. In general, it's continuous. It means that you can find the frequency or the spectrum at every frequency need 0.1, 1.1, minus 1.2. But by the way, you don't have to worry about the negative because if you have a real function, always you will find that the spectrum magnitude, even function, like the one to the right, equal to the one to the left. The positive frequency amplitude is equal to the one negative frequency. The amplitude are equal, so we like even. But the angle, it's odd. For example, if you have at frequency 10, the angle equal 90, at negative 10 will be equal negative 90. So that's, you have to keep in mind that and put in the notes. That's it for today. Start tomorrow to work on your P-Lab. No more extension.